Mais um dia, mais uma live, começando aí mais um domingo de revisão. Quer dizer, tem um tempo que eu não faço domingo de revisão, mas a gente vai fazer hoje. Eu quero começar visitando a Threads, né? Lembrando Threads, que faz tempo que eu não vejo. Esse volátil aqui hoje dá pra gente ver também. Virtual Threads, acho que tá ligado com Threads, dá pra colocar aqui também. E aí, o que eu posso ver aqui? Posso ver sobre modos e options também. Por enquanto vai ser isso, depois a gente vai revisando outras coisas. Não sei qual que é o melhor de se revisar, mas por enquanto vai ser isso aqui. Vou só fechar a porta e já volto. Vamos ver então threads aqui. Eu gosto de pegar esses artigos que estão aqui, geralmente eles são bons.
Say that the thread is just
Esse aqui é o mesmo vídeo daqui.
Program or process, as programs are also sometimes referred to, at a time, only one at a time. In this video, I will give you a quick overview of Java multithreading and concurrency. But before I do so, I will just give you a quick overview of the history of multitasking and multithreading in general. Just a quick heads up, this video is an introduction to Java concurrency and multithreading on a conceptual level. Therefore, it does not contain any code examples. However, this video is part of a playlist of videos about Java concurrency, and later videos in this playlist do contain code examples. If you check out the description below the video, you will find a link to this playlist as well as to my textual Java concurrency tutorials, which also contain code examples. In the early days of computing, a computer could only run one program or process, as programs are also sometimes referred to, at a time, only one at a time, right? So that in that case, if you were working inside of Word or something similar like that, and you needed to make some changes to something inside Excel, you would have to close down Word and jump into Excel and change the thing you needed to change, and then close Excel again, and then open Word up again. And that kind of workflow quickly becomes quite annoying for the user. To solve this problem, multitasking was invented, and multitasking basically means that now the computers can run more than one application at the same time. But since the CPU can only execute one program at a time, the CPU or the computer solves this problem by executing one application for a little bit of time, then switching to another application and executing that for a little bit of time, then switching to another application and executing that for a little bit of time, then switching back to the first one and repeating. This way, it will appear to the user as if all of these applications are actually running at the same time, even though they are actually only running one at a time, but the switches are so fast that the user cannot see or feel the difference. It feels as if all the applications are running at the same time. I said that it was the CPU that is switching between these applications here, these tasks, but in reality it is a combination of the CPU and the operating system, right? So the CPU executes the operating system, and the operating system then switches between the tasks here. And modern day CPUs have some built-in features that makes this task switching easier for the operating system. Multithreading is the same principle as multitasking, except multithreading happens within an application. So instead of having one thread of execution inside of an application, you can actually have multiple threads of execution inside of an application. So for instance, an application might both be downloading a file in one thread and playing music in another. And the way that threads are executed is similar to how tasks or applications are executed. First, one thread here gets to execute a little bit on the CPU, and then the operating system or the application, depending on who controls this thread, switches to another thread, and now this thread gets to execute a little bit. And now we switch completely, the operating system switches completely to another application, and then that first thread here inside of this application gets to execute a little bit on the CPU, and then it switches to another thread, and then this thread gets to execute a little bit on the CPU, and then we switch completely out of this application and back to the first one here, or to any other application running on the computer. Modern computers typically come with multiple CPUs in, or CPUs with multiple cores in, which in practice is the same thing. So on a modern computer, you might actually have multiple CPUs executing these applications. And in that case, that means that some of the applications might actually be running at the exact same time because they're being executed by different CPUs. For instance, here, this application here might be running at the exact same time as this application down here because they are executed by different CPUs. Now, each CPU may still context switch between applications and internally between threads within each application. So some of these applications and threads are not exactly executing at the same time, but some of them will be because of the multiple CPUs, right? By the way, in this diagram, it looks as if each application is only executed by a single CPU, but that is not necessarily the case. It is possible to have an application running which has one thread executed by one CPU and another thread executed by another CPU down here, for instance. And in that case, each of the threads might actually be executing at the exact same time because they are running on different CPUs. And this is often the case in software that requires a lot of compute power. For instance, 3D rendering software, video editing software when the final video has to be exported, or computer games. Now that we have discussed what multithreading is, let's dive deeper into why multithreading is a good idea. First of all, we can achieve better CPU utilization with multithreading. Take a look at this example here. I have an application which has one thread running here, and at some point here, the thread needs to load some data from disk or from network. Now, while this data is loading from the disk, the CPU cannot really do anything within this thread of execution up here. It needs the data before it can continue. But instead of simply being idle and wasting these CPU cycles, the computer can switch to another thread and execute whatever work this thread needs to get done. And at some point, when the CPU or the operating system feels that it is time to switch back, or like when the full data here is loaded, it can switch back from this thread down here to the first thread, which can now continue running because now the data has been loaded into memory. In this way, we can better utilize the CPU while I/O tasks are running. Another benefit we can achieve with multithreading is better I/O utilization. Look at this example here. First, we have a thread running within an application, and now this thread needs to load some data from the disk. And then it spends some time processing this data, and after that, it loads the next data, and then it processes that data, etc. Now, as you can see, we are actually switching between full utilization of the CPU and full utilization of the network I/O, but we have these gaps in between here and here and here and here where we are not using either. And imagine then that we have another thread. It's not the same thread, but another thread running, which you can see here. This thread up here is idle, right? The CPU is idle up here while it's loading data from the network. So we can have another thread here which has asked for some data, which it can now process. and then this one can now load data while this thread up here is not loading any data from the disk or network, right? It's actually utilizing this empty space here. This idle I/O bandwidth is being utilized by another thread, and so and thus it can switch between these two threads that are utilizing the I/O at different times. So when one is waiting for I/O, the other one is using the CPU, and when the other one is using the CPU, the other one can use the I/O, and the disk or the network. And actually, you might even have two threads using for instance, the network card at the same time. For instance, if they are both downloading a file or waiting for a file to download from a server which is slow, you might actually be able to start multiple I/O downloads at the same time from different threads. And so in this way, we can not only better utilize the CPU, but also the I/O capabilities of the computer, the bandwidth to the disk and to the network. A third benefit we can get from multithreading is higher application responsiveness as perceived by the user. Imagine you have a GUI application, a graphical user interface. The user clicks on a button here, it starts some processing here, and then it starts a long-running task which runs in the background, and when the task is finished, the thread can go back to updating the user interface and responding to further input from the user. Now, in this period here, the thread is busy executing the long-running task, and thus it cannot respond to the user's input or update the user interface. And that means that in this time period here, the application will appear unresponsive to the user. Now, to avoid that, we can start the long-running task in a separate thread down here, right? And thus the CPU will switch forth and back between the long-running task in the separate thread and the main UI thread in the UI thread. And so it switches forth and back, and to the user it appears as if the application is still responsive, because at all these times here the application still responds to the user's input. But sooner or later, because this application will probably not use all of the CPU time, sooner or later enough CPU time will have been allocated to the long-running task in the separate thread down here, and so it finishes, and then the user interface can be updated saying, oh, by the way, this file is now fully downloaded, or whatever else this long-running task in the background is. In a computer that contains multiple CPUs, the long-running task here might actually be running on its own CPU, which is a different CPU than the one executing the main UI thread. And thus, we might start the action here, like this is just a little bit of initialization, then the long-running task starts. And because this task is running on a different CPU, this thread is running on a different CPU, the main UI thread can continue undisturbed on the other CPU, or its own CPU, which is executing this thread up here. So now the long-running task is actually executing at the exact same time as the main UI thread is continuing to respond to input from the user. As you can see, multithreading is really beneficial to us in computer programming. However, it is not without its problems, without its issues that we need to learn how to handle. First of all, the first model that appeared for concurrency was a shared mutable state model in which threads could read and write the same memory inside of the application. However, this type of concurrency model leads to possible race conditions, invisible writes.
Tá, isso aqui, os problemas acho que dá pra gente ler aqui. Cadê? Ele não fala dos problemas aqui? Tá, não quis falar. Vamos ver o virtual threads desse mano aqui. Ah, não, aqui tem um...
time, but this thread is not actually doing anything, so it will just start and stop immediately. I will show you in later examples how to actually execute some code inside of this thread. There are actually 4 different ways to specify what code a thread should run. And the first way is to create a class which extends the thread class and then override the run method. And I will show
Aqui
you
eu
a
tava,
little bit later how
tava
this
praticando
example
thread nessa...
is actually working, or that it is actually working. The second way is to create a class that implements the runnable interface.
Ah, lembrei. Eu lembro que tinha isso, que tinha... Você podia colocar extends thread ou extends runnable. E extends runnable era mais recomendado. Eu lembro que o extends runnable era mais recomendado, mas eu não lembro por quê.
And then pass an instance of this runnable to the constructor of the thread. And then when the thread is started, it will appear here. It will then execute the run method. And I will just run it here so that you can see that.
Aqui ó. Aqui eu criei um objeto, né? Do runnable, né? Através de uma classe anônima. Aí eu usei uma lambda para definir ele. E aí, aqui eu simplesmente usei o thread runnable target. E que dei start e executei 2 de uma vez. Interessante.
It is actually working. However, this is, as you can see, the run method is executed, it prints my thread running and my thread finished. Now, even though this is working, this is not considered as nice as implementing the runnable interface instead. So I have just shown you that it is possible, but I would recommend that you use one of the runnable interface implementation methods in your own applications. The second way is to implement the runnable interface. And in this example here, I have created a class called myRunnable, which implements the runnable interface.
Criei um objeto que implementa. Vou criar outro objeto, colocar runnable R2 igual. Eu só vou copiar esse código aqui. Que eu acredito que você não precisa usar chaves aqui. Coloca var r2 igual new thread. Deixa eu colocar r2 aqui. Coloca aqui var thread 2. T-start, T2 start. Colocar R desponta 2 desponta. Aqui foi o R2. R2 de novo. 2. Eu queria colocar ele pra ficar embaixo. Aqui. Legal. 2. Agora o R. Não sem ordem, né? Que eu tô fazendo o processo de multithreading.
And from the runnable interface, you must implement the runner's class.
Implementar runnable interface com uma classe anônima.
And
Foi o que eu fiz, né? Bom, eu lembrei do thread mais ou menos. Agora vamos ver o virtual threads.
virtual threads is a new construct that has been added to Java from Java 19. In this video, I will take a quick look at how they work and how virtual threads are different from platform threads in Java. Before I jump into the code, let me just go through a little bit of theory regarding virtual threads. The existing threads in Java will from now on be referred to as platform threads. A platform thread is executed by an operating system thread. A virtual thread is executed by a platform thread, which is again executed. Before I jump into the code, let me just go through a little bit of theory regarding virtual threads. The existing threads in Java will from now on be referred to as platform threads. A platform thread is executed by an operating system thread. A virtual thread is executed by a platform thread, which is again executed by an operating system thread. When a virtual thread is first created, it is not yet mounted within a platform thread, so it is not yet being executed. Instead, it is being queued up internally in the Java platform, and when there is a platform thread that is ready to execute the virtual thread, then it will take the thread, the virtual thread, and mount it inside itself and then execute it. The virtual machine keeps a couple of platform threads ready to execute virtual threads, and it will typically keep approximately the same amount of, or the same number of platform threads ready as you have CPU cores in your computer, or in the computer that your application is running on. But normally you don't have to worry too much about that unless you want to tweak it. In some cases, when a virtual thread performs some operation that blocks it, for instance, it makes a network call using blocking I/O, or it calls some concurrent construct or data structure. But normally you don't have to worry too much about that unless you want to tweak it. In some cases, when a virtual thread performs some operation that blocks it, for instance, it makes a network call using blocking I/O, or it calls some work in the computer that your application is running on. But normally you don't have to worry too much about that unless you want to tweak it. In some cases, when a virtual thread performs some operation that blocks it, for instance, it makes a network call using blocking I/O, or virtual thread. In some cases, when a virtual thread performs some operation that blocks it, for instance, it makes a network call using blocking I/O, or it calls some concurrent construct or data structure that blocks the thread while it is waiting for a signal from another thread. In that state, the virtual thread is blocked and it can then be unmounted from the platform thread. So the virtual thread is blocked and it can then be unmounted from the platform thread. So it is parked here on the side, and the platform thread can then take another ready virtual thread and execute instead. Once the response comes back either from the remote service that has been called over the network, or the virtual thread here is unblocked by via this concurrent data structure via a signal from another thread, then such a virtual thread here that is blocked can then be put back into the ready queue down here and eventually get scheduled on the platform thread 2. This means that we can utilize the platform threads much better in the cases where the virtual threads here, or the logic that we are executing, is making blocking network calls, or have a lot of coordination with other threads via concurrent data structures. So instead of constantly blocking the entire platform thread, we now only block the virtual thread, and then the platform thread can simply execute another virtual thread in the meantime. Additionally, virtual threads are much more lightweight in terms of how many resources, especially memory, RAM, that they require compared to a platform thread. And that means that while it would be kind of hard to maybe run 1 million platform threads within the same application, it is actually possible to run 1 million virtual threads within the same application, because 1 million virtual threads do not need as much memory as 1 million platform threads would. Now let us have a look at some code examples so you can see what it looks like when you create a virtual thread. To create a virtual thread in Java, you call the thread.ofVirtual method, which is a static method, and then you call either to start the virtual thread immediately, or the ofVirtual method when you create a virtual thread. To create a virtual thread in Java, you call the thread.ofVirtual method, which is a static method, and then you call either the start method to start the virtual thread immediately, or the unstarted to create a virtual thread that has not yet been started. Both of these two methods take a runnable as parameter, and that is the same runnable that you would use with a normal platform thread. A Java virtual thread is also an instance of a Java-lang thread, possibly a subclass of Java-lang thread. I'm not quite sure about that. But as you can see, I can just use thread as the type of the variable referencing the virtual thread. A virtual thread is also an instance of a Java-lang thread, And so in order to start and unstart a thread, I simply call start, just like I would on a normal platform thread. And it is also possible to join a thread once it is started, simply by calling the join method, just like you would on a normal platform thread. And join will block the thread that calls join until the platform and unstart a thread. I simply call start, just like I would on a normal platform thread. And the virtual thread here has finished executing. Up type thread. I've set the virtual thread count to 100,000, and then I simply iterate in this loop, repeat in this loop 100,000 times, and create a virtual thread. And this virtual thread is simply calculating some result inside of a loop and then printing out the result. So, but all the virtual threads will arrive at the same result, but that is not what is important. What is important is to see that it's possible to create 100,000 of them, and after that you can see they are immediately started because we call start, and then join them all and then wait for all of them to finish, and to see that this example will finish in a reasonably timely fashion. Okay, so finish. Does not seem to have any memory problems at all. Running these 100,000 virtual threads. In fact, it seems to be going reasonably fast. And you can see even a little bit out of order down here. So you do not have a guarantee that the threads are executed, the virtual threads are executed in the exact order you create and start them. But now you see it finished.
Vamos dar uma olhada em módulos agora. Pra dar aquela revisada legal. Virtual Threads é tipo uma thread dentro de uma thread que ela pode ser dividida em outras threads, dependendo do coisa, pode ser desmontada, né? Dentro da thread original, né? Aquele mapa que o cara mandou foi bem bom. Vamos ver aqui. Vamos ver agora sobre optionals, pra gente encerrar.
stars that are more brilliant than anything you've ever seen on the clearest nights here on Earth. And then you pass into the lunar sunrise over the lunar surface, and it must be an awe-inspiring sight.
Legal, cara. O
I
optional
can't wait to see myself.
achei bem útil, né? Complexo. Mas é bom dar aquela refrescada na memória. Pra semana que vem a gente vai revisar generics, cara. Faz muito tempo que eu não gosto de generics. E é algo que é bastante utilizado, né? Então a gente tá revisando, fazendo uma revisada foi bem denso. Revisada pesada mesmo. É isso. Isso aí fora. Amanhã, como sempre, tem mais. Vou dar aquela enroladinha de 20 segundos pra dar 51 minutos. Então, não sei o que eu posso fazer nesses 15 segundos que restaram. Vou dar uma olhadinha no meu código. Ficou muito bom esse código aqui, né? Então, pô, essa música é muito boa. Vou fazer uma playlist com ela.